This animation opens onto a shifting mathematical landscape where a single cubic curve is alive on the screen at every moment. Each frame presents the solutions to the cubic equation, and as the animation advances, the coefficients change through a wide range of integer values. What the viewer sees is not just a sequence of equations, but a continuous exploration of how algebraic structure reveals itself through geometry. The horizontal and vertical axes remain fixed, marked by dashed reference lines at 0. This stability gives the viewer a reliable frame of reference so that all attention can be focused on the curve itself. As the cubic sweeps across the plane, it immediately becomes clear that the leading coefficient A governs the overall direction of the curve. When A is positive, the graph descends on the left and rises on the right. When A is negative, this behavior reverses. Watching the animation, one might pause to wonder how such a simple sign change can completely invert the curve's global behavior. If you find this content helpful for your math learning journey, consider subscribing and liking the video. It helps more math students discover it. As the coefficients B and C evolve, subtler transformations begin to emerge. The curve may stretch, compress, or bend into more elaborate shapes. Sometimes forming pronounced twists, and sometimes appearing almost monotonic. In some frames, the curve seems to hesitate, flattening briefly before changing direction. At this point, the narrator might quietly invite the listener to ask, "How does this bending relate to the number of times the curve might cross the x-axis?" A green dashed horizontal line marks, sliding smoothly up and down as the constant term changes. This line anchors the curve's vertical position and makes the y-intercept visually explicit. When the green line shifts, the entire curve follows. Watching this motion, the listener may begin to sense that vertical translation alone does not change the curve's fundamental shape. But does it affect how many times the curve intersects the x-axis? Those intersections are highlighted by red points whenever they occur. These points mark the real roots of the cubic equation. Sometimes only one red point appears, standing alone where the curve cuts through the axis. At other times, 2 or even 3 red points appear simultaneously. Their sudden appearance or disappearance is one of the most striking features of the animation. As roots merge or separate from one frame to the next, the narrator might gently ask, "How does the number of real roots change as the coefficients shift? Does this feel random, or can a pattern be sensed visually?" In frames where 3 real roots appear, the curve typically bends twice, forming a clear S shape with 2 turning points. The listener may notice that the curve must dip below and rise above the x-axis multiple times for this to happen. This invites another reflection. Are there particular geometric features, like the presence of two turning points, that seem necessary for three real roots to exist? Conversely, when the curve crosses the axis only once, it often does so while remaining monotonic, never turning back. Is this coincidence, or a deeper structural rule revealing itself through motion? Occasionally, the animation shows moments where a red point lingers at the x-axis before splitting into two or collapsing into one. These fleeting frames suggest repeated roots where the curve touches the axis without fully crossing it. The narrator might quietly draw attention to this moment, asking, "Can you see how the curve's shape changes exactly when roots merge or disappear? What must be happening geometrically at that instant?" In the corner of the screen, the coefficients and root information are updated continuously. This text grounds the visual experience in algebra, yet the animation encourages the viewer to rely increasingly on intuition rather than calculation. Over time, patterns begin to feel familiar. Certain combinations of coefficients seem to favor multiple crossings, while others almost always produce a single real solution. The listener may start asking themselves, is it possible to predict the number of real roots just by looking at the curve's overall shape, even before reading the numbers? By the end, the animation no longer feels like a sequence of isolated equations. It becomes a conversation between algebra and geometry, unfolding in time. The narrator leaves the viewer not with answers, but with sharpened perception, and with the lingering sense that the behavior of cubic equations is something that can be seen, felt, and anticipated, not merely solved. If you found this content helpful for your math learning journey, consider subscribing and liking the video. It helps more math students discover it. Thanks for watching.